Alright, it's section 11.3, the last one in the textbook. Title of the topic, the Binomial Theorem. And if you're thinking, how does this relate to the stuff we just did in the earlier part of chapter 11? Well, it kind of really doesn't, but it uses some small part from, I guess, our earlier chapters study, so therefore it's here. But nonetheless, it's a nice way to end off because it's all about patterns. Here's something called Pascal's triangle. Pascal, of course, was a famous French mathematician. You can read more about him on Wikipedia if you wish. But this is his famous triangle. And I have only given you the first 4 rows. I'm hoping that you can kind of find the pattern and then fill in the next few rows. Okay? So take a look and see what you can do. I'll give you a hint. This is a 1. That's a 1. Probably a 4. Probably a 4. The magic number in the middle is a 6. Okay? Maybe that will help you complete the next row. 1. And a 1. 5. And a 5. The things in the middle, if you guess 10 and 10, you're right. One more. How about a 1? 6. And we'll end off with 6 and 1. And if you understand the pattern now, how about 15, 20, 15, 6 and 1. Okay. I want to ask you right now to think about this triangle and list any patterns you see. Okay? And I want you to do that right now. So take a few moments, stop the video, list the patterns. Go. And if you're thinking I'm going to give you the answers, I'm not. So keep your ideas on paper, keep them in the back of your head, but we're moving on to this part. So it's called the Binomial Theorem, so I'm going to ask you to expand some binomials. Binomials, of course, means 2 terms, so I'm going to just use x and y to represent those 2 terms. Let's do x plus y all squared, and I will quickly do that for you. That's what, x squared plus xy plus xy plus y squared. And if you can't do this now, you shouldn't be in grade 12 math. Okay? X plus y cubed, you might be thinking, well, that's just x plus y times x plus y all squared. Well, x plus y all squared from just what we did 2 seconds ago is x squared plus 2xy plus y squared. So we'll go ahead and now expand. X cubed plus 2x squared y plus xy squared. And then we have plus x squared y plus 2xy squared plus y cubed. We'll try to simplify that by collecting like terms. So x cubed. I think these are like terms, right? So 3x squared y. Here's like terms. 3xy squared plus y cubed. Cool. And then we'll do x plus y to the power 4. And that's just x plus y times x plus y to the power 3. We know what x plus y to the power 3 is, since we just did that. So I'm going to copy that from the previous question. Okay. And then expand and collect like terms. X to the power 4. 3x cubed y. 3x squared y squared. Xy cubed. X cubed y. 3x squared y squared, 3xy cubed, plus y to the power 4. And this simplifies to x to the power 4. Looks like it's 4x cubed y. How about 6x squared y squared? 4xy cubed? Y to the power 4. Okay. Now, we're looking at the binomial theorem. We're going to be doing even bigger exponents, like x plus y to the power of 10, perhaps. So I'm not going to be asking you to multiply this out like this every single time. That'll take way too long. And math is beautiful because it's all about patterns. So, do you see any patterns looking at the powers of x? And then do you see any patterns in the powers of y? And then do you notice anything about the coefficients in the binomial expansion? So look at the 3 examples that we've just done. Do you see any pattern in the x's? Seems like the terms start at the highest power, right? See, look, x squared, then becomes x, then nothing. X cubed, then x squared, then x, then nothing. X4, x cubed, x squared, x to the power 1, nothing. Seems like you start with, I don't know, highest power. And it goes down by 1 with each successive term. How about the powers of y? Well, y seems to be just the opposite. Nothing, 1, 2. Nothing, 1, 2, 3. Nothing, 1, 2, 3, 4. Start at power of 0 and go up by 1 with each successive term. Okay, what about the coefficients? Know anything about the coefficients? Well, x plus y squared, the coefficients, let me just quickly show you, are 1, 2, 1, right? X plus y cubed, 1, 3, 3, 1. X plus y to the power 4, 1, 4, 6, 4, 1. Where have you seen these numbers before? Yeah, the Pascal's triangle. Looks like they are from Pascal's triangle. So, let's see if we can put all this stuff together, okay? Let's turn the page. So I want you to compare Pascal's triangle with a coefficient in the binomial expansion. And there you have it. X plus y to the power 1, 1 and 1, 1, 1. X plus y squared, all right, 1, 2, 1. Cubed, 1, 3, 3, 1. 4, 1, 4, 6, 1. 5, 1, 5, 10, 10, 5, 1. Well, let's use our pattern now to try to expand x plus y to the power 6 without doing it the long way. Well, we know that we should be using the Pascal's triangle for our coefficients. So I guess our next row would be 1, 6, 15, 20, 15, 1. So 1, 6, 15, 20, 15. I forgot one, didn't I? Sorry. 6, 1. 6, then 1. Well, what's the pattern again? Yeah, start with the highest power of x, x6, then we reduce x5, x4, x3, x2, x, and nothing. And what we do with the y's? Yeah, nothing, then 1, then 2, then 3, then 4, then 5, then 6. Let's add them all up. There you have it, ladies and gents. X plus y to the power of 6 expanded in one step. Cool. So no longer do you have to do all that expanding stuff. You can now just use this pattern and Pascal's triangle rows to help you out. Now, what's so important about that? What's more important now is let's see if we can use our answer from above to now expand something more complicated, not just the x plus y, but let me change it to this, 2x minus 3y. Well, what we're doing here now is you're really just saying replace our x from above with 2x and also replace y from above with minus 3y. So let's do that. Instead of 1x to the power 6, it's now 2x to the power 6. Still have the 6 there, but now instead of x to the power 5, it's 2x to the power 5 times y, which is negative 3y. We've got the 15 still. Instead of x to the power 4, it's now 2x. Instead of y, it's now negative 3y to the power 2. We'll continue on. 20, 2x to the power 3, negative 3y to the power 3. And then plus 15, 2x to the power 2, negative 3y to the power 4, plus 6 times 2x times negative 3y to the power 5, and then plus negative 3y to the power 6. That's what we have. Now we should simplify. So 2x all to the power 6. 2 to the power 6 is 64. 64x to the power 6. Plus 2 to the power 5 is 32. 32 times 6 times negative 3. I think that's actually a negative. Do that on your calculator, please. Should be negative 576. X to the power 5y. Okay. The next part, we'll expand out. 15 times 2 to the power 4, that's 15 times 16 times negative 3 squared, which is 9. That's 2,160. X to the power 4, y squared. 20 times 2 cubed, that's 8. 20 times 8, 160 times 3 to the power 3, that's 27. That's minus 4,320. X cubed, y cubed. Continuing on, I said it's 15 times 2 squared is 4. That's 60 times negative 3 to the power 4. That's negative 81. Multiply that out. 4,860. And then there's x squared, y to the 4. And then the next term, 6 times 2 is 12. Times negative 343. Minus 2,196 x y to the power 5. And finally, negative 3 to the power 6 is just 729 y to the power 6. Done. And there's your expansion of 2x minus 3y all to the power of 6. Okay. Let's turn the page. If you're wondering about what those patterns were like, and to confirm your patterns on the first page, well, Here's another way to think about Pascal's triangle. Okay, if you were to do combinations, 0 choose 0, on your calculator you would have found that that equals to 1. 1 choose 0 is also 1. 1 choose 1 is also 1. 2 choose 0 is 1. 2 choose 1 is 2. 2 choose 2 is 1. 3 choose 0, well, that's just 1. 3 choose 1, that's 3. 3 choose 2, that's 3. 3 choose 3, that's 1. Now, if you don't believe me, put these all into your graphic calculator. Try. Fill out the rest. So you've just built Pascal's triangle using combinations. And so I was asking you those patterns. Well, here's two of them that you can kind of see. There's something called the symmetric pattern. So let's look closely at this row here for the symmetric pattern. 5 choose 2, right? That's 10. Well, that's symmetric to 5 choose 3. Why? Because out of 5 people, if I choose 2 winners, there are 3 losers. Well, if I once again choose 3 losers, there are 2 winners. Same thing. So that's why it's symmetric. Right? These are also symmetric. And then the last ones are symmetric. Right? Now, there's also something called a recursive pattern. I think this is the one that most of you probably thought about when you create the Pascal's triangle the first time. 5 choose 2, once again, is this number 10. How do I get 10? Well, that comes from 4 choose 1 and 4 choose 2, the two numbers directly above it. And that's this recursive pattern. So 4 choose 1 plus 4 choose 2 equals 5 choose 2. So, just for your information. But in general, why do we use this Pascal's triangle? It's because those are the coefficients of my binomial expansion, or binomial theorem. So remember that pattern, what do? Well, we start it with x to the power n, and then we had y with nothing. And then we had x to the power of n minus 1, remember we reduce, and then y goes up by 1. And then we had, I think, something like x to the power n minus 2 with now y squared. And this pattern kept going, right? Kept going all the way to the end, which was, well, I'll write it down here, plus, how about x to the power of 1, and we had then y to the power of n minus 1, and then our last term, x to the power of 0, which we won't write, but we have y to the power of n, right? Recall again that the powers of x start at the highest and then go down. Powers of y start at 0, then go up. And then the numbers in front, the coefficients, are now given by the binomial expansion. N choose, in this case 0, n choose 1, n choose 2, and so on and so forth until here. This is going to be n choose n minus 1. Notice, by the way, that last part is always the same thing as the power of the y. And this will be then, of course, n choose n. Okay. This is called the binomial theorem. And it can be used to expand any power of a binomial expression. And you'll use this in calculus next year. So that's why it's here. But before we continue further, let's just take a note at a few things. How many terms are in this binomial theorem? If it's raised to the power n, they are actually n plus 1 terms. Think about that, right? Go back to like x plus y to the power 2. There are 3 terms. X plus y to the power 3. There are 4 terms. So, in general, x plus y to the power of n means there are n plus 1 terms. The number of objects, which I call k, selected in the combination of n, c, k, or r, can be taken to match the number of factors of the second variable. Right? See this 0? That matches the 0 power. The 1 matches the power of y. The 2 matches the second variable, the power of 2, and so on. K is equal to the exponent on the second variable, right? Same idea. Same thing as before, pretty much. The sum of the exponents in any term of the expansion. So if I look at one particular term, let's say over here, and I said, what's the sum? Well, this is n minus 1. This is 1. So n minus 1 plus 1 is just n. Over here, oops, this should have been 2, by the way. This is n minus 2. I will change that. Make it look nice. How come no one stopped me earlier? Erase. Okay, it should be n minus 2. Okay, so in this case here as well, if I were to add these exponents, n minus 2 plus 2 is just n. So the sum of the exponents in any term of the expansion is n. Now, this next part, start, because we'll use it. The general term, which I call t kth plus 1, has what type of form? Okay, so if I just wanted one particular term, what form is it? Well, it's of this form. N C K x to the power of n minus k y to the k. Now be careful. You see how the general term is t sub k plus 1? So let me just try to illustrate this for you, alright? If I want the third term is the equivalent to t sub 3. Now in this format of k plus 1, that means, therefore, k plus 1 is equal to 3. So what's k? K is actually equal to 2. So therefore, when I use this formula, the third term is actually n choose 2, x to the power of n minus 2, y to the power of 2. Okay? And that is correct, because if I look now at my third term in this expansion, that's what I got. Okay? So please be careful here. That's why it's t kth plus 1 has this form. Okay? I'll box this because this is important. I'm going to put a little star here next to the k plus 1 so that we know. Okay? Alright. Now, let's just go on to our next examples. We've got example number 2, which I'm going to ask you this. I've got this interesting expression. A minus 2a to the power 6. This is the binomial because there are two terms. So in this case, I'm asking you how many terms are in this expansion. So I'm not asking you to expand them all, but I'm just asking you how many terms. Because it's raised to the power 6, we know how many terms are going to be. It's one more, so there must be 7. Right? Done. Now I'm going to ask you to use the binomial theorem to determine the first 3 terms. Now remember how we did the binomial theorem? Yeah, it's n choose 0, x to the power of highest value, which is 6, y starts at 0, right? So forget that. Then we have n. By the way, n is what in this case? It's 6, right? So then we have 6 choose 1, x to the power of 5, y to the power of 1. And then we have now 6 choose 2, x to the power of 4, y to the power of 2. And those are the first 3 terms. That's the general form of writing it. Now we have to apply it to this expression. 6 choose 0, that's just 1. So 1 times x is the first term in our expansion, because it's kind of like x plus y to the power of 6. So that means x is just equal to our a value, and y is just equal to our negative 2 over a value. So that's a to the power of 6. 6 choose 1 is 6. That's a to the power of 5. And here's our y, so it's negative 2 over a. Then we have 6 choose 2. That's 6 times 5 is 30. Divided by 2 is 15. A to the power of 4. And then negative 2a all squared. So we'll continue to try to simplify this. So we have a to the power of 6. Oops, this was a minus, because I have the 6 times the negative 2. So how about negative 12? a to the power 5 with the a in the bottom, that's a to the power 4. 2 squared is 4 in this case, so that's 15 times 4 is 60. A to the power 4 and a squared, so that's a to the power 4 divided by a squared, which is just a squared. And there you have it, the first three terms of this binomial expansion. Well, what if I said, just find the fifth term? Would you go ahead and list out all five? You could. Or you can use that lovely formula that we just created, the t kth plus 1 formula. Remember that one? nck, x to the power of n minus k, y to the power of k. Well, remember, this is the fifth term, so I want t sub 5, which means what is k? I'll do it over here. So that means k plus 1 equals to 5. Therefore, k is actually equal to 4. So we want nc4, x to the power of n minus 4, y to the power of 4. What's n in our example here? Yes, it's 6. I'm going to write this as 6. 6 choose 4. 6 minus 4. And when we do that, 6 choose 4, what's that? You can use your calculator. I will use my brain. It's 15. X is just a. Remember how we said that earlier? So a to the power of 2. And y is negative 2 over a, all raised to the power of 4. 2 to the power of 4 is 16, right? 16 times 15, that's 240. Then you have a squared all over a to the power of 4. So I think that's just 240 over a squared. And that's the fifth term of the expansion. They might ask you some other question like this, where it says determine the term that contains this this term of a to the power of negative 4. You could just write out the whole expansion, but of course that probably takes too long. So what do you think we can do to help us out? Well, let's use that tk plus 1 formula again. Let's see what we can do. I'll copy it one more time. Because I'm learning it for the first time, I like to copy things out. Just makes life a little bit better, and it gives me a chance to review. Okay, we don't know the term, so we don't know k in this case. Okay, so we don't know k. We want to find k. That's our goal. So our goal here, find k. Well, we do know what n is. That's 6, right? So 6 choose k. Weird. We do know what x is. We replace that with a, and it's now 6 minus k. And we know what y is as well. It's negative 2 over a, and we replace that with k. Well, let's go ahead and see if we can do some expansions and see. Okay, I'm looking for the term that contains a to the negative 4. So we have 6ck, a to the power of 6 minus k. And over here we have negative 2 to the power of k, and that a in the denominator can be written as a to the power of negative 1 to the power of k. Now, we're just concerned with the variables. So this part we're concerned with, this part we're concerned with. So let's combine them together. If I were to combine them together, that becomes a to the power of 6 minus k, or 6 minus 2k. Now, I know a to the power of 6 minus 2k. I'm looking for the term that contains a to the power of negative 4. So, I guess a to the power of 6 minus 2k must be equal to a to the power of negative 4. So since the base is the same, therefore the exponents are the same, 6 minus 2k must equal to negative 4. Negative 2k equals to negative 10. K equals to 5. And therefore, which term is it? If k equals to 5, it's t of k plus 1. So this must be t6. So therefore, it's the sixth term. The sixth term has a to the power of negative 4. one last example and we're done. So, I'm going to turn around. I'm going to say now one of the terms in this expansion of 3x minus b to the power of 8 is this crazy number, negative 1,701,000, x to the power of 5, y to the power of 3. It's your job here to find what b is. Okay. Now once again, when you know a term, let's use that formula. T sub k plus 1 equals to n c k, x to the power of n minus k, y to the k. What else do we know in this case? Oh yes, our x in our binomial expansion has been replaced with 3x. And our y has been replaced with negative b. Okay, and we know n also is power of 8. So let's put this in. N, C, K, x, which is now 3x to the power of 8 minus k, times y, which is negative b, to the power of k. Now, this is equal to what? Well, I guess it's equal to our term. So our term here is negative 1,701,000, x to the power of 5, y to the power of 3. Okay. X to the power of 5. Well, how do we get x to the power of 5 on the right-hand side? The only way you can do that is if the exponent related to the x is also 5. Okay? So comparing the x to the power of 5s, here's what we get. So just comparing. On the left side, we have x to the power of 5. On the right side, we have 3x, 8 minus x. I think you can conclude here that the k value must equal to 3 in order for the right-hand side to be x to the power of 5. Right? K equals to 3, so that the right-hand side can come back, can be x to the power of 5. That's great, because now I know what k is. So if I know what k is, then I can do even more stuff now, right? So knowing this, I'm now going to go back to the previous statement, and now I can say negative 1,701,000 x to the power of 5 y cubed is equal to 8c3. And then this now becomes 3x to the power of 5 times negative b. Come on. Negative b to the power of 3. So let's continue further and try to simplify. 8 choose 3. 8 times 7 times 6 over 6, so that's 56. Three to the power of 5, that's just 243, so that's 243 x to the power of 5. And this is just negative b cubed. And this is supposed to equal that big ugly number on the left-hand side. Well, it looks like the x to the power of 5's cancel out. 56 times 243 times negative 1 is negative 13,608. That must be equal to multiply that by b cubed. That equals to negative 17,010,000 y cubed. So we'll divide both sides by the negative 13,608. And then we'll have 125, I believe, y cubed equals to b cubed. And if I want to solve for b, therefore b equals to the cube root of 125y cubed. How about b being equal to 5y? And there you have it. Okay, that's how you can go backwards, try to find out one of the terms in a binomial expansion. We're done.